Welcome to the Tim Booker book sharing channel. Like, subscribe, and hit the notification bell so you don't miss our updates. Let's explore the world of books together.
Today, I'm going to decipher a book for you called Helgoland, subtitled Making Sense of the Quantum Revolution. Published in May 2023, this book, as the title suggests, delves into quantum mechanics. The author, Carlo Rovelli, stands as one of the rare scientists of today who can articulate quantum mechanics in an accessible and engaging manner. Carlo Rovelli, a theoretical physicist, made a significant contribution by co-founding the loop quantum gravity theory, a branch stemming from string theory. This direction of research aims to unify general relativity and quantum mechanics. To put it in a more relatable context, if you've seen the TV show, The Big Bang Theory, the character Sheldon is a genius physicist delving into string theory. Professor Rovelli could be seen as a scientific figure akin to Sheldon, but with an even higher emotional intelligence. Rovelli doesn't just limit himself to cutting-edge physics, he continuously writes popular science books, disseminating knowledge of physics to the masses. Prior to this, Helgoland, we've interpreted his works like Reality is Not What It Seems, The Order of Time, and The Adventures of a Physicist's Intellect. However, Helgoland, the book I'll interpret today, doesn't solely revolve around scientific discoveries. Rovelli's primary focus lies not in how quantum physics alters the world but in how it changes humanity's perception of the world. Quantum physics undeniably reshapes our world. It enhances human understanding of nature, from the colors in the sky to brain functions, from the origins of galaxies to atomic movements. Countless questions in the world find clearer answers due to quantum physics. It also influences human lifestyles. The latest technologies, such as smartphones, computers, solar panels, and nuclear power, heavily rely on quantum physics theories. Physicists, chemists, biologists, and engineers leverage quantum physics in their daily work. Nevertheless, the impact of quantum physics on the world surpasses these aspects. Rovelli recalls his undergraduate days when he chose physics because, in his words, he vaguely suspected that behind the boring high school physics, behind the stupid exercises on springs, levers, and rotating balls, there hid a pure curiosity trying to understand the essence of reality. During university, classical physics courses made him feel like he touched upon something, with their succinct elegance. However, facing quantum mechanics, he felt bewildered yet exhilarated. It wasn't until many years later, after reading numerous books, engaging in various discussions, and arriving at many uncertain conclusions, that he finally wrote Helgoland. This book delves into more questions than answers because even today, scientists cannot entirely comprehend the principles behind quantum mechanics. Many phenomena seem baffling. Yet, within these mysteries lie opportunities for humanity to overturn its perceptions of the world. Each time humanity gains a clearer understanding of the world, stemming from something seemingly baffling, it's akin to a paradigm shift, from assuming the Earth is flat to discovering it's round, from geocentrism to heliocentrism, and even acknowledging our insignificance in the vast cosmos. Every time humanity grasps this world more distinctly, it arises from something seemingly baffling. Actually, I think a more fitting title for this book could be How Quantum Physics Alters Our Perception of the World. In this episode, we'll take a roller coaster ride through the mind, following this book, to comprehend the forefront thoughts of current scientific discoveries. We'll first go back to the inception of quantum mechanics because right from the start, it perplexed scientists immensely. Understanding this journey will provide a clearer view of which aspects of our understanding of the world quantum physics has shaken. Next, we'll explore what modern scientists currently contemplate about the world. Part 1. How did quantum physics shake our understanding of the world? Let's first examine how quantum physics shook our understanding of the world. Since its inception, quantum physics has puzzled scientists immensely. Before this discipline emerged, there was a time when the fundamental principles governing the universe seemed crystal clear. Everything, in essence, appeared to be composed of microscopic particles of matter, driven by just a handful of forces. You might have heard of a famous incident in the history of physics. In 1900, Lord Kelvin delivered a lecture at the Royal Institution in London titled 19th Century Clouds over the Dynamical Theory of Heat and Light. In his speech, Lord Kelvin mentioned that the edifice of physics was nearly complete, with only minor patches left. However, there were still two small clouds, as he described them. But just 5 years after this lecture, traditional physics was disrupted. The resolution for the first cloud led to relativity, and the resolution for the second cloud led to quantum mechanics. Even the advent of relativity helped people gain a clearer understanding of the world. In an expansive space, particles moved under the influence of forces, pushes and pulls. Faraday and Maxwell introduced the concept of electromagnetic fields. A field existed dispersed in space, exerting forces between distant objects. Einstein refined this theoretical framework by demonstrating that gravity could also be encompassed within the concept of a field, which was the geometrical existence of spacetime itself. This summary was both clear and elegant. However, with the emergence of quantum physics, the world appeared chaotic once again in the eyes of scientists. Our story begins here. In the summer of 1925, a 23-year-old man proposed a theory to explain some perplexing phenomena in physics. This young man was Werner Heisenberg, and the story of quantum mechanics began with him. What peculiar phenomena did Heisenberg seek to explain? At that time, a renowned scientist named Niels Bohr discovered formulas that could predict the characteristics of chemical elements. For instance, when an element was heated, the frequency and color of light it emitted could be predicted. This was a remarkable achievement at the time. The problem was that although Bohr's formulas perfectly matched experimental observations, scientists had no idea how to explain them. According to Bohr's formulas, electrons within atoms could only move in specific orbits, carrying specific levels of energy. It's akin to astronomers telling us that the moon orbits the Earth but can only travel along two specific orbits, one at a distance of 360,000 kilometers and the other at 410,000 kilometers. Any distance closer or farther isn't permissible. What's more bizarre is how does the moon transition between these orbits? Shouldn't the moon gradually move closer or farther? Not at all. The moon directly jumps from one orbit to another. Today, we know this phenomenon as quantum leaps in quantum mechanics, a peculiar behavior of tiny particles. But at that time, scientists attempted to understand it based on the laws governing celestial bodies. The manner in which electrons jumped between specific orbits seemed too bizarre. How did electrons move within atoms? Why were these specific orbits significant? What caused these inexplicable leaps from one orbit to another? Scientists of the time believed that atoms constituted the fundamental building blocks of all matter. So, if these questions remained unanswered, understanding the fundamental principles of matter seemed impossible. Bohr and his colleagues spent over a decade investigating this problem, yet they gained no ground. It seemed there was no reasonable force that could explain the peculiar orbits and leaps of electrons. However, these orbits and leaps could accurately predict atomic phenomena. It was perplexing. As a young physicist, Heisenberg also became ensnared in this inscrutable problem. Like others, he attempted every method but found no success. Until 1925, when he made some breakthroughs. Heisenberg's idea was bold yet straightforward. Since no force could explain the bizarre motion of electrons, why not refrain from seeking a new force and instead base our thoughts on known forces, such as the electrical force that attracts electrons around the atomic nucleus? If the laws governing electron orbits couldn't be identified, then why not continue employing known principles of mechanics without changing them? The only change required was in how we perceive electrons. Discard the analogy to celestial motions and no longer regard electrons as objects moving along specific orbits. In short, since we couldn't currently comprehend how electrons moved within atoms, Heisenberg suggested abandoning the description of electron motion. Only describe what can be observed externally, such as the intensity and frequency of electron emission. Reinterpret electrons based on these observational data. Heisenberg used matrices for calculations. He sent the calculation results to his friend Pauli, saying in a letter, "Everything is still very vague, and I don't know what this means, but it seems that electrons no longer move along orbits." Around the same time, another scientist, Erwin Schrödinger, attempted to write equations describing the enigmatic behavior of electrons. After Schrödinger formulated his equations, people revisited Heisenberg's work and had a sudden realization: their mathematical calculations predicted probabilities. Whether it was Heisenberg's or Schrödinger's quantum theories, both predicted probabilities, not deterministic events. From this point onward, quantum mechanics began to confound people. Even Niels Bohr, the scientist who unlocked the door to quantum mechanics, said, "Anyone who isn't confused by quantum mechanics hasn't understood it." Part 2, where does the peculiarity of quantum physics lie? What exactly puzzled scientists about quantum mechanics? There are primarily three aspects. Firstly, the state of particles can superimpose. The most bizarre aspect of quantum mechanics is its uncertainty. A particle may exist in one position and simultaneously in another. Physicists call this phenomenon quantum superposition, which challenges the certainty in scientists' minds. Many scientists refuse to accept such outcomes, with even Einstein stating, "God does not play dice." Secondly, observation affects outcomes, as if particles can sense when they're being observed. The results obtained while observing and not observing can vastly differ, causing scientists to question the boundary between subjectivity and objectivity. Thirdly, energy carried by particles comes in discrete amounts. Later, physicists discovered that the reason electrons in atoms must occupy specific orbits is that only in these positions can electrons possess the appropriate energy, meeting the requirement of discrete packets. In other positions, the energy carried by electrons might not be in whole packets, which contradicts the laws of physics. The name of quantum theory derives from quantum, meaning discrete packets of energy. Previously, people believed the world should be continuous, but quantum mechanics revealed that the world might be discontinuous even at the smallest scales. Quantum mechanics affirmed the discontinuity in the world. Traditional physics led people to believe that the world was deterministic, governed by laws unaffected by human influence, and continuous. However, quantum mechanics shattered humanity's prior understanding of the world, informing us that this belief was incorrect. But quantum mechanics hasn't provided the correct answer. Presently, scientists have formulas that can be mathematically validated, and results observed in laboratories. Yet, the interpretation of these formulas and results remains unresolved. According to these formulas and results, some incredibly perplexing conclusions can be inferred. Part 3, New Perspectives from Scientists on the World. At this point, you might feel deeply puzzled. What exactly is this world? Unfortunately, there might not be a definite answer at the moment. Since the birth of quantum mechanics, physicists have proposed various ideas to address these three puzzles mentioned earlier. However, none of these ideas have been completely verified. There might be new theories in the future that refine or even overthrow current notions. Nevertheless, from a different perspective, this is precisely what you should understand. This represents the forefront of physics exploration, where the current answers appear partly obscure at the boundary between what's known and what's unknown. Next, let's follow Rovelli and explore the forefront of this world's exploration. Let's see what the current scientists think about the world. Let's first consider scientists' contemplation of superposition, which might bring to mind the famous thought experiment, Schrödinger's cat. Imagine a sealed box containing a cat. Inside the box is a radioactive device that, within an hour, might decay or might not. If it decays, it triggers a device that breaks a vial of poisonous gas, killing the cat. Before you open the box, the radioactive substance is in a quantum superposition state of decayed and not decayed. So, before opening the box, does the cat, a macroscopic organism, also exist in a quantum superposition state? This thought experiment links microscopic quantum uncertainty directly with the macroscopic world. It forces you to confront the understanding of the quantum world, but how do you face this problem? Hence, there's a quote from Hawking, "When I hear about Schrödinger's cat, I reach for my gun." Schrödinger's cat leaves physicists feeling unable to confront this world. Part 4, Why do many scientists endorse the multiverse? Hence, some physicists proposed a conjecture: when we conduct this experiment, the universe splits into two. In one universe, you open the box and find the cat dead. In another universe, you open the box, and the cat is alive. Yes, the parallel universe hypothesis you've seen in movies is what scientists propose to explain quantum mechanics. Each parallel universe shows a definite result, but when these parallel universes are superimposed, it becomes a superposition state. Sounds crazy, doesn't it? Yet, numerous distinguished physicists and philosophers believe that the hypothesis of parallel universes is the answer within quantum theory. This hypothesis best explains the peculiar phenomena observed by scientists. This bizarre feature of superposition is already challenging to comprehend, let alone the discontinuity and the observer's influence. How do we explain these features? In this book, Rovelli proposes a viewpoint he terms relational interpretation. Part 5, Rovelli's concept of relational interpretation. What is the relational interpretation? Rovelli believes that exploring which orbit an electron occupies when it isn't interacting with any object is meaningless. The electron doesn't follow an orbit because its physical attributes are determined by its interactions with any other object, such as the light it emits. Without interaction, the electron has no characteristics. This is a radical step. It implies that we should view each object solely based on its interactions with other objects. When an electron doesn't interact with any other object, it lacks fundamental physical attributes. No position, no velocity. The crux here lies in physicists' understanding of the world, all based on observation. Whenever we observe, matter interacts with us. Thus, the displayed result inevitably carries human factors. The world might not necessarily be influenced by humans, but the world we see unavoidably bears the influence of humans. The world we perceive is, in essence, a network of interactions between various materials and us. Let me offer another analogy to help you grasp Rovelli's thinking. We know, of course, that the Earth isn't the center of the universe. Yet, the observable universe today is a sphere centered around the Earth. It's akin to you holding a torchlight in a pitch darkness. The range you can see is a circular area centered around yourself. So, even though we know the Earth isn't the center of the universe, we can only see a part of the universe centered around the Earth. Beyond this, we're unable to see. Likewise, Rovelli implies that perhaps in quantum mechanics, matter possesses characteristics unrelated to humans, but we can't see them. Because once we observe, we inevitably involve ourselves, and what we can see is only the result of our interaction with particles. This might sound perplexing and not easily acceptable. Whether you agree or disagree, it doesn't matter. After all, Rovelli himself hasn't claimed this as the definitive answer. However, following this line of thought might make the perplexities brought by quantum mechanics appear much clearer. For instance, why is the world discontinuous? Some scientists propose a theory called quantum bitism. Bit borrows from the world of computing, representing information in discrete packets. What does quantum bitism imply? Physics doesn't describe the essence of the world, it's the information we have about the world. Perhaps due to certain human limitations, the information we receive about this world arrives in discrete packets. Hence, the world we can recognize arrives in discrete packets. As for the true nature of the world, we remain clueless. Moreover, why do calculations in quantum mechanics often yield probabilities, and the position or velocity of a particle can't be completely determined? Considering the relational interpretation, Rovelli believes that quantum physics and traditional physics have two essential differences. The first, the finite amount of relative information that can be obtained from an object. The second, interaction with the same object always yields new relative information. You might ask, doesn't that contradict? If interacting with the same object always yields new information, then if I interact for a sufficient duration, can't I acquire all information? The key is, when we obtain new information, some old information becomes invalid, turning into irrelevant data. So, although we constantly gain new information, the information quantity remains finite. Part 6, can we fully understand the universe? Furthermore, following this notion further, can humanity ever fully comprehend the universe? Rovelli's answer is negative. Imagine conceptualizing the entirety of something, which actually means picturing how it looks from outside. Therefore, envisaging the whole universe involves picturing us standing outside the universe, observing it. The issue is, we lack such an external viewpoint. We exist within the universe, and any descriptions we have of the universe originate from within it. There's no world observed from the outside, there exists only the world's internal, partial, and mutually reflecting perspectives. The world is a mutual reflection among these perspectives. If we continue deducing from this line of thought, it might surpass physics and enter the realm of philosophy. This book indeed devotes considerable content to Rovelli's philosophical musings. However, I believe these contemplations are more subjective and personal, so I won't delve into them. If you're interested, the e-book version of this book is available, and you can explore it further. Nevertheless, Rovelli's contemplation on the relationship between physics and philosophy is worth sharing. Rovelli believes that physics and philosophy are closer than people imagine. He says, physics is the place where the intertwining between the structure of reality and the structure of thought is the closest, and where this intertwining continually undergoes evolutionary trials. Moreover, he thinks that with the development of physics, new philosophies will inevitably emerge. A philosopher once asked Rovelli how experiments conducted in a laboratory using metal and glass could have the power to shake people's deeply ingrained impressions of the world. Rovelli's reply was, "Weren't those deeply rooted impressions derived from the early humans manipulating stones and wooden pieces?" So, that's it for me decoding Carlo Rovelli's Helgoland for you. Because it involves cutting-edge scientific discoveries and thoughts, after listening to this book, you might end up with more questions than answers. It's inevitable, scientists like Rovelli also find themselves more puzzled when dealing with quantum mechanics. But that's okay. In the book, Rovelli does provide some things that we can firmly believe in. Firstly, because quantum mechanics is such an evolving discipline with so much uncertainty that even scientists are hesitant to claim complete understanding, all those things branded with the label of quantum medicine, quantum holistic theories, quantum spiritualism, are entirely baseless. The world of quantum might be a bit mysterious, but Rovelli assures you that it has nothing to do with the mystical cosmos. Secondly, Rovelli believes that future scientists will need to be interdisciplinary. His reasoning aligns with the relational interpretation, since our observations of the world inevitably carry human factors, the boundaries between disciplines are hard to call objective, they're merely hierarchical divisions made by us to understand the world. But the real world doesn't come in hierarchical divisions, which means we need knowledge that doesn't respect these divisions, and we need scientists who can transcend them. Thirdly, scientific exploration demands the courage to overturn oneself. Science often demands that we relinquish what's considered unassailable and impervious in our understanding of the world. It requires us to accept the stark disparity between reality and our imagination, to not fear the profound unknowns, and to dare to cast our gaze into the abyss. In the book, Rovelli says, science is a way of exploring the world with fresh thinking, a critical and forward-looking power that dares to resist authority, a power capable of changing its own conceptual foundation and reshaping the world from scratch. I'd like to conclude this audio session with a passage written by Rovelli. I believe this passage provides an answer as to why each ordinary person needs to take some time to listen to such a mind-boggling book, why we should understand questions that don't yet have answers. Our love and sincerity come naturally to us, we are born with an innate thirst to know more, to keep learning. Our understanding of the world is continually expanding. At the boundary of knowledge, our quest for knowledge burns. We yearn to explore the subtle textures of space, the origins of the universe, the essence of time, the phenomena of black holes, and the operation of our thoughts. Now, at the forefront of what humanity knows, we are about to sail into the unknown sea. The mysteries and beauty of the world shimmer before us, dazzling our senses. That covers the essence of this book. Congratulations on finishing another book. Thank you all for your support and attention. Please subscribe to the Tim Booker channel, like, and share this valuable knowledge with your friends. Let's combine wisdom and practice to achieve our financial goals and create a better future. Thank you, everyone. Goodbye.